siamo? Good. So, welcome back. It's the second week and lesson number 11, I think. Today we talk about how to do physics at the light of the discussion about time that I gave in the last lecture. So remember that the last lecture was about different meanings that time has, and I distinguished the sort of relational time, Aristotelian, Cartesian time, location with respect to events, from Newtonian time that later evolves into generalistic time in the gravitational field. There are chairs there and there. So usual physics, Newtonian physics, as well as special relativistic physics, there's always a time variable, there's a t, which is more or less what a clock measure, right? T measure a clock, and we have a number of variables that describe what goes on. These variables, the set on which they vary is called a configuration space. Configuration space, and the game of dynamics is to see how they vary in time. So time is crucial for just start talking about dynamics. It's evolution of the variables in time. The standard notions that one uses is the notion of phase space. So the Qi and the momenta form the phase space, gamma, which is crucial for doing dynamics because evolution is not determined by the value of this at some time, but the value of this and the velocity of their momenta at some time. And dynamics is given by a Hamiltonian in many possible ways, one being an Hamiltonian, which is a function of phase space, so it's a function of Qi and Pi. Which via Hamilton equations of whatever you want defines the evolution. So the classical equations of motion are the equations for these variables here. If you want, in configuration space, a motion, so this is the configuration space. A motion is it's a line here. These things evolve in time, where you have a parameter t along this line, and the intervals in t are identified with the interval of the clock. Right? That's the standard thing. And in the quantum theory, this becomes operators. In fact, these and these becomes operator, namely these of these form a non-commutative algebra. They have eigenstates. You take a maximum commutative set of eigenstates. Let's say there is a maximum commutative state of eigenstate labeled by quantum number Qi for simplicity, like it happens for a particle. And then the quantum dynamics is captured by the transition amplitude from some initial Qi initial and initial time to some final Qi final and final time, T final, which is Qi final e to the I over h bar, T final minus the initial h q I initial. Okay, simply. And of course, this transition amplitudes can be written a la Feynman as a path integral of a path in the limit in which the phenomenon you're considered has action small with respect to h bar. So in the limit in which you can take h bar small, this functional integral is dominated by the classical trajectories, and so on the functional integral, the dominant trajectory is the classical one. So the amplitude is approximatively proportional to I over h bar, the classical action of the physical trajectory that starts here, and goes there, which is what I call the Hamilton function. Qi initial, t initial, Qi final, t final. So the Hamilton function gives the first approximation to the quantum transition amplitudes, and the Hamilton function is the solution of the Hamilton-Jacobi equation. Okay, so this is just a 1 minute summary of classical mechanics and quantum mechanics when you have time. All right? Now, why I said that? Because physically, if you take this thing here and another clock, this is another wonderful clock from Daniel, and they indicate the same time, which say they should, if they're a good clock. And now you all know that if you do that, okay, you wait a little bit and you bring them back together, they don't indicate the same time anymore. Right? So is this T the one up or the one down? You can say, well, I don't know, is the one that didn't move. Or you can say the one along the geodesic, which in fact is not the same thing, right? Let's do with not with that. I don't want to break, Danny, your. If I keep this here and I throw this up and down, the one followed geodesic is this one, right? Because that's free falling. So which one is the real time? It's not the one of the clocks. You don't know the clocks that are constantly bounced up. What's the point? The point is that, so if I have a clock which indicates 12 o'clock, another which indicates 12 o'clock, I wait until it indicates 3 o'clock, and this one I move it up and down, and when it comes back I indicate 2 o'clock. This clock I call TA, this clock I call TB. Which one is time? Neither, but both, either. There isn't a single time in general relativity, right? The time clocks measure different durations depending on where they are, but every possible position, path, speed gives a different time, and we have to deal with the fact that we have clocks of different manners. So we don't have a preferred time t, and in fact, in a general situation, there might be not even one possible global way of measuring time. There are many. Change happen. Clocks change. I talk. Things happen. Clock change one with respect to the other one. So Aristotelian time, Cartesian time, time in the sense of locating some happening, some events with respect to other events, of course is there. That's what we're talking about. We're talking about physics, namely events, namely processes. But these processes don't have a preferred single t variable to label them in general. So we need a formulation of classical mechanics and to do quantum gravity formulation of quantum mechanics where we don't start from a preferred Newtonian time, just because in general relativity there is no preferred Newtonian time. There's no preferred Newtonian clock. So this structure does not work. We have to change it, not much, just a little bit, just twinkle it a little bit to make it a little bit more general, to include the possibility of talking both of TA and TB on equal grounds, or of different variables on a set of variables on equal ground. And to do that, the natural thing is to change a little bit this structure by taking the time variable and sort of treating it on the same ground as the other variables. If you think what is going on in this scheme is that we have these variables, but we have also this variable, the position of the handle of the clock. So let's just treat it like the other ones, and start from an extended configuration space, C extended, which has a set of variable QA, which in the Newtonian case would be, let me put it in blue here, would be the set of Qi and T. But where I don't, I treat the Qi's and T on the same ground. I don't make a distinction between all of them. Which means that I here runs from 1 to n, where n is the number of degrees of freedom. I here goes from 1 to n, where n is the number of degrees of freedom, where A here runs from 1 to n plus 1, where n is the number of degrees of freedom. So I am including the independent variable among the variable that I use for the distinction. And we want to just extend this language in this manner. Well, this is pretty easy. So the phase space, there is an extended phase space, which QA PA is sort of 2 dimensions more than the phase space. So I call this gamma extended, which correspond if there is a Newtonian time, this will be QIT, PI, and a PT extra variable conjugate time, which you will not be surprised to see that it turned out to be the energy, or more precisely minus the energy. It's a funny minus that come naturally in this game here. Now, the dynamics in this language is not given by the Hamiltonian, but is given by a single function on the extended phase space. So a function of QA PA, which is has many names. It's called the relativistic Hamiltonian by some people. We call the Hamiltonian constraint. By some other people, and has other name. I suppose the Hamiltonian constraint is the more well known. Now, if you have how do you do the dynamics from here? I mean, you know how to compute the evolution from the Hamiltonian. How do you do the dynamics from C? Let me start from a rather abstract general way, because it's conceptually particularly clean. You can start with the Hamilton-Jacobi equation in this setting. And the Hamilton-Jacobi equation is the equation C QA ds over dqa, where S is a function of QA equals 0. So that's a relativistic or covariant relativistic Hamilton-Jacobi equation. And if you know how to solve this equation, if you have a family of solutions of this equation here, you know the solution of the equation of motion. And in particular, there is a family of solutions that you can write for a quantity SQA initial, SQA final, requiring that it is a solution of the Hamilton-Jacobi equation in both set of variables, initial and final. Okay, and that's a Hamilton function of the theory. So this is a Hamilton function. is defined to be a solution of the Hamilton-Jacobi equation in both initial and final variable. And how does it determine the evolution? By the standard property of the Hamilton function, if you take the derivative with respect to the initial and put it, so this is a function, remember, initial and final position, and you put it equal to some constant PA initial, this derivative here is a function of QA initial and QA final. So you get a relation between initial position, initial momentum, and final positions. So for each set of initial positions and initial momentum, which is a position in gamma extended, point in gamma extended, you need a relation between all the variables, all the final variables. All right? Notice that since this equation here, this function here satisfies the Hamilton-Jacobi equation, that's what we require, this derivative here are the momenta. So all variables p, all variables initial position, initial momentum that sits into equation satisfies the relation C QA PA equals 0. So all the motion that you considered are determined by point in the phase space, which are in the subset of the phase space determined by this equation here. In fact, another way of viewing this is that the phase space, gamma extended, this is a symplectic space. There is Poisson brackets on it. It's a conjugate. There is a symplectic form dqa dpa. When you write this equation, you have a surface, which is called the constraint surface. In a symplectic space, when you have a constraint surface, the symplectic form reduced here has null directions. Its null direction draws some lines. These lines are the motions. If you project it down to the configuration space, which is half of the phase space, you get motions in the extended configuration space. You get the motions here. Now, careful. These motions are very much similar to what I drew before in the standard configuration space, except that in the configuration space, I assumed to have a given time labeling the points here, and I know the equal clicks of the time. Here, there is no preferred variable along. Or if you want the relation between this and this, these are in an n-dimensional space. This is an n+1 dimensional space. So this picture here is actually the evolution in time of the Qi when I have a Newtonian time. So what is the relation between this and the usual story? Well, it's very easy. In the Newtonian case, so let's look at the Newtonian case, and then we'll see the non-Newtonian case. And the Newtonian case is when C, QA, PA. Remember, in the Newtonian case, QA is QI and time. So the Newtonian case is when this has the form PT, the momentum conjugate to this variable here, plus some function of QI, PI equal, when this is equal to that, and then the equation is this being equal to 0. Well, this is the Hamiltonian. This is the usual Hamiltonian. So you see, this is the Hamiltonian. Its value is the energy. So this is minus the energy, as I said. And the Hamilton-Jacobi equation, which I wrote, if C has this form, reduces to the standard form of the Hamilton-Jacobi equation, ds over dt plus h of qi ds over dqi equals 0. So this is the standard sort of no-relativistic form of the Hamilton-Jacobi equation, right? Which is how this general relativistic form reduces when the relativistic Hamiltonian and the Hamiltonian constraint have this form. And in particular, the Hamilton's function solution of that is a function of qi initial, t initial, qi final, t final, which satisfy the Hamilton-Jacobi equation in both set of variables, and so on and so forth. And if you do that, if you write ds over dqi, which is a function pi of q initial, t initial, q final, t final, equal a constant, pi, then you get for each initial position and initial momentum, initial time, and for each final time, a value of qi. So you can extract from that qi final as a function of time per each point in the usual phase space, qi pi. Each one of these give a motion, a standard motion. So you get the usual story when the relativistic Hamilton function has this form, but you have a more general setting in which you never need to say which one is your independent variables. Variables evolve one is a function of the other one. That's a key language that can be used, in fact, that has to be used in a general relativistic context where there is no big click, click, click time. In the universe, there is no time that clicks that give a single Newtonian time of the unit. So throw this away, and I should have put this away. I am not paid by Coca-Cola, but if Coca-Cola wants to pay me because I've shown this, I'm happy. Is that clear? This is a crucial point in which there has been years and years of discussion since the 60s how to deal with time in quantum gravity, and where is time in quantum gravity. Time in the sense of change, full series, right? The trajectories, but time in the sense of a preferred variable, in terms of which the evolution is described, is not there because it's not there in classical GR. It's not needed because it's a totally covariant language without preferred time that makes sense. And we'll see that in quantum gravity, one is forced to have this general language. I'll write this equation for general relativity very soon, explicitly. Now, a few other considerations about this formulas to make it a little bit more concrete. Let me keep that part, which is general, and erase this one. I shouldn't use this. And if you have questions, this is a good moment. I'll give you a few super simple examples to make this concrete. Then add some detail and then do the quantum thing. So, example 1, with Newtonian time, the simplest possible example you can imagine is one free particle Okay, the extended configuration space, you can call the variables position and time. Okay, and the relativistic Hamiltonian is pt plus 1 over 2m p square, of course. So the Hamilton-Jacobi equation is ds over dt plus 1 over 2m ds over dx square equals 0. And a Hamilton function, which is two set of variables which are both solution of this equation, it's immediate to write down. The Hamilton function is m q initial minus q final square. I think there is a 2 t, I forgot the sign, t final minus t initial. And you see that it satisfies this in both set of variables, because if you take a derivative with respect to t, you get a minus and a square. If you take a derivative with respect to q here, we call it x, you get a 2 that cancel this 2, and you get you cancel the square. So when you square, you get back the square and m square, which cancel with this m, and the 2 is back from here, so this equation is solved up to the sign that I hope is right. And of course, from here you get immediately the solution of the equation of motion, because if you write dx over dq equal p, let's see what it gives, ds of dq in, say, equal p in, p initial, you get m q initial minus q final, the 2 cancel with the 2 down, divided by that, so equal pi t final minus t initial, you divide by m, and you have q final is this plus q initial. So the final position is the initial position plus the velocity and the time lapse. Okay, but of course you don't need to revert. The point is that the crucial point is that this equation here gives a relation such that given initial and final, given initial position and momentum, you get a relation between q and t at all times. Then nothing forces you to think that this is an evolution of q and t. It's just a relation between q and t. So I say, what do you gain? Well, example 2, a little bit more. Also, you know very well, this is an example with Newtonian time, but with many possible equivalent Newtonian times. So without a preferred Newtonian time. Example 3 will have no Newtonian time at all. Preferred Newtonian time. This is also something you know very well. So 1 free relativistic particle, special relativistic particle. Then the extended configuration space is Minkowski space. Okay? And the relativistic Hamiltonian, or the constraint relativistic Hamiltonian, is simply p square minus m square equals 0. Okay? So, or if you want, c is p square minus m square. And if you go through that, it's easy to write down the Hamilton function, it's easy to write the solution. And in Minkowski space, the motions, of course, are all the, you find out all these lines here. What's the point here? The point is here, you can say, well, of course, I mean, x0, the coordinate of Minkowski space is time, and this, say, x1 is the position of the particle that changes with time. This is a particle that doesn't move, this is a particle move, faster, almost the speed of light. So nothing prevents you from identifying x0 as the Newtonian time. But this is in a Lorentz frame. In another Lorentz frame, you would call time x tilde 0, which is just x0, gamma x0 plus gamma beta x1. So which one is time? The time of this frame or the time of this frame, which are related by this equation here? Well, you don't need to say. The dynamics doesn't need to say which one is time. It's perfectly well defined. It gives you the trajectory on the basis of the structure here. Third example, and now it's a little bit more interesting. It's a system without time at all. Without Newtonian time. At all. Now what do I mean? Well, I mean that if there is a Newtonian time, in time the motion goes forever. So time goes from minus infinity to plus infinity. It's global in time, continuous. So here is a system that can be formulated in this manner, but cannot be formulated in the usual manner, with a single evolution in time. And it's very simple. The extended configuration of space has two variables, say time and position. Well, let me not use time because, so let me call them A and B. A and B. And let them Newtonian, so it's function of QA and PA. So let me do explicitly A, B, PA, and PB. And it's the following one. PA square plus PB square plus A square plus B square minus a constant. Let me call it E, the constant. Now it takes a minute, it's in the books if you want to do the explicit calculation, to see that the motions in the extended configuration space, so in AB, the motions do something like that and form ellipses. All the motion are ellipses, more or less squeezed, more or less big. And so there is a one parameter family of ellipses that solve that. So if you look at the motion for a short while, you can think that this is B evolving in A. So you can call A time. And you have an equation that says explicitly how B evolves in A. But the problem is that this comes back. So A times come back and circles back to itself. So obviously, there's no way to write this as a standard evolution system in the Newtonian way that I wrote at the beginning. Right? Just clearly. Because a standard system, Q may change as you want, but never comes back in time. Right? So this doesn't happen. Well, this happens. So clearly, this small example shows that this language is not just a reformulation of standard Newtonian mechanics, it's a slight extension of standard Newtonian mechanics. It's complete equivalence to standard Newtonian mechanics in the cases in which this is PT plus an Hamiltonian, but it's more general. It includes other cases. And these other cases include the relativistic cases and general relativity. Okay? Questions? All clear? It's all simple. This is simple stuff, right? This is, but But unless this is digested, quantum gravity becomes incomprehensible. People hang on to Newton time, to Minkowski space, to global time, to time at infinity. Otherwise, we cannot do physics. A large amount of work in Newtonian in quantum gravity has a difficulty of needing to hang on some notion of Newtonian time. There's no need to hang on a notion of Newtonian times. Classical mechanics perfectly well defined. And we'll see in a moment that quantum mechanics is also well defined. Now, still about that. Some more points also to clarify, to connect with many things in the literature. If you have extended configuration space, the motion is a line there, which just give a relation between the different variable q1, q2, and the other. So how one changes a function of the other one, like here. I mean, the possible value of b when a has this value are these two. The possible value of b when a has this value, there is none. Just if a has this value, the system never has this value. Obviously, since the physical meaning of these curves in extended configuration space is just a relation between the variables, it makes no physical sense to choose a special parameterization of the curve itself. I can parameterize this with a, with b, or with some functions, whatever I want, the angle, but any parameterization is good. However, nothing prevents me of choosing a parameterization, arbitrary, and call it tie, and this is what in the literature is called parameter time. Which careful is not any of the variable that you measure, unless you fix it somehow, and you can choose it to be a here. It's just double value, but still. But you can choose it completely as you want, and when you choose it as you want, it has no direct geometrical physical meaning whatsoever, but it's made convenient to parameterize the variable themselves. And of course, we are used to this because we learn it to do this game in special relativity classes all the time. In special relativity, if you have a particle moving, the motion of the particle is given by the position as a function of x0. This is where the physics is. At every time x0, measured by a clock in a certain reference frame. So this x0 gives the position of the clock in a certain reference frame. And then in that reference frame, the particle is at some different value of x1. But we know that this is not a convenient way of describing the motion of the particle. A convenient way of describing the motion of the particle is all four variables as a function of time, where mu is 0, 1, 2, 3. And this is an arbitrary parameter. And we can write a action for an evolution in tau of this thing here, and you know the action is m, the integral in d tau, square root of x dot mu x dot nu, where x dot mu is just the derivative dx mu over d tau, and indices are lower and raised with a Minkowski metric here. Mu, thank you. Thank you. And you know that if you write the Euler-Lagrange equation for this action here, you get exactly this trajectory here, parameterized how? In any arbitrary parameterization. In fact, the Euler equation, Euler-Lagrange equation of this action here don't fix the parameterization. This action is minimized by any Okay, the end of last lecture was not taped for technical problems, so let me repeat what was in the last, what was in the end of last lecture. What I was saying is that in the extended configuration space, the motion has no natural parameter at all, but one can parameterize it with a arbitrary parameter tau, and a good example where this is done routinely is in the in the dynamics of the relativistic particle, where the action is m, the integral in this d tau of the square root of x dot mu, where x dot is the derivative of this with respect to tau. And this action is invariant under change of parameter tau. So if I send tau in any function tau prime of tau, the action does not change. So the action from here to here as a function of some initial x mu initial and some final x mu final, it only depends on x mu initial, x mu final, and not of any parameterization of any initial and final tau there. Now, if I start from this action and I do the Hamiltonian treatment of the theory doing a Legendre transform on this action here, what I discover is that the Hamiltonian is zero. This is an immediate calculation. The Hamiltonian is p mu x dot mu minus Lagrangian in general, and p mu is the derivative of the Lagrangian with respect to x mu, which is immediately computed here, is m x dot mu over square root of x dot x dot. Take the derivative, I get a 1 over square root with a 2, and then a 2 from the derivative here. So if I use this here, I get m x dot square over square root x dot mu over square root of x dot mu minus the Lagrangian, which is m the square root, which is exactly the same thing. So this is equal to that. This is 0. So the Hamiltonian is 0. And where is how do one does the Hamiltonian theory? Well, very simply, the Hamiltonian is 0, but the in the phase space being x mu p mu, being coordinatized by x mu p mu, by definition of the p mu that satisfies this equation here, we see immediately that p mu square is x dot mu divided by x dot mu is 1. So p dot square is 1. So it follows from that p square is equal m square. So this is 1 and just remain m square. So on this phase space here, there is a constraint which is p square minus m square equal 0. So this has actually properly to be interpreted an extended phase space, which is what it has to do. These are 4 Lagrangian variables and 4 momenta for 3 degrees of freedom, because a particle is 3 degrees of freedom, not 4. And we fall into the structure that I described of a general covariance system, where there is what I call the relativistic Hamiltonian, and on an extended phase space, which has all the information, and we don't need to know which one is time variable. More importantly, the tau parameter is arbitrary. Everything physical here is independent of tau. The Hamilton function as a function of some initial x mu and some final x mu is just a function of these, not of any initial tau and final tau. Now, why this is important? Because these parameters here should not be confused with time. And when we go to general relativity, which I'll discuss in detail in the next lecture, and I'll do the Hamilton-Jacobi formulation of general relativity and the general covariant formulation of general relativity of the dynamic of general relativity in the next lecture. In general relativity, the variable is g mu nu of x and t, but this t here is this tau here. So the t here, it's a arbitrary parameterization along space-time, which is completely arbitrary, has no direct interpretation, is not one of the variables of the theory at all. So this is like tau there, a arbitrary parameter to which no measurement corresponds, and in particular has nothing to do with the clock. The clock, what the clock measures is the integral on a world line of square root of g mu nu dx nu along the world line, and there is one clock for every world line. So in space-time, we have world lines, and these are observables in the extended phase space or configuration space, which are function of these quantities here. So these metric components here are the variables which we can observe. So in C extended or in the corresponding phase space, not these, not x and t. And when Einstein wrote general relativity, the big struggle he went through in between 1912 or before until 1915, the way he put it, the great difficulty was understanding the meaning of the coordinates, because the key point is that these have a completely different physical meaning that the coordinates of special relativity. The coordinates of special relativity are clocks and rods. These are not clocks and rods. These are arbitrary things which one can do without. Like for a special relativistic particle, one doesn't need tau. One can work just with x mu and think as evolution as x in function of x0 and just never talk about tau. Here one can do general relativity without ever talking about t. And in fact, the Hamilton-Jacobi equation for general relativity and the Hamilton-Jacobi formulation of general relativity that I do in the next class will be completely without t. Which doesn't mean that time is frozen, nothing happens. Things happen. General relativity describes space-time evolution, but without need of parameterizing things with this variable here. Dynamics is the relative evolution of things, not in how things evolve in a single variable. Thank you.